Thank you for Yungli for the introduction. So hereby is this webinar. I promise I will not take this 1 hour and a half and leave some time for lunch, so we can enjoy our day. So the title is here like this: quantum accelerated supercomputing, which means we have CPUs or high performance computers, and we have this different modalities of quantum computers. And right now, the EuroHPC joint undertaking is integrating many of them already, and there is like one machine that's up and running right now. It's called the VLQ. Maybe you heard about it. So the main purpose here is that how to use these machines, which is like quantum accelerators, together with HPC in a problem that is already well available and well represented in high performance computing. So that's a simple use case for that. And it's more of an atomistic simulation use case. So people who are familiar with DFT calculations, density function theory calculations, or this kind of computational physics are relating to this one. But also, if you don't have any experience into that, this can be also a good overview for the use case and to learn about that. I will not really give so much depths into DFT and lose many audience. So the main, challenge of this use case is that we have, material simulations consume already HPC resources in a big chunk of it, and using working perfectly classical methods. Yet these methods are full of approximations. So there's what you call it like you want a higher accuracy when it comes to reaching this chemical accuracy and things like this. So for that, even theoreticians made something called like a Jacobian ladder of heaven, where whenever you reach a higher accuracy, you are more closer to heaven, and this means more computational resources needed for that. Of course, not every key use case needs that, but for some specific use cases, it could benefit a lot, especially, for example, related to drug discovery or drug design and things like that. So hereby in this one, I think quantum computing can offer an opportunity here where it can accelerate such HPC paradigm or HPC calculations to run using quantum methods or quantum native methods, which could bring a value here to the to your workflow as as atomistic simulation scientist. And as an example here, I wanted to bring it to you as how you can have a workflow working from like A to Z of how to examine environmental friendly alternatives to corrosion inhibitors for both aerospace and automotive industries. And here, when I'm talking about this materials that help or are coated on the body of an aeroplane or a car in order to protect it from corrosion, and then it will last longer, and you're happy with your car. And the goal here is to demonstrate this end to end, as I mentioned, and see how you can integrate the quantum part into the high performance computing. Then you reach to solve a material science problem. So maybe you have seen this a lot when you see, blog post or a Jupyter notebook about how to calculate the ground state energy for hydrogen. But then this is quite, proof of concept all the time. But maybe you want to do something more useful, more to bring it more to your research and things like that. So that's why I made this effort a little bit last year into how to really go beyond this, and I'm not the first one here. It's like I'm just based on studies and things like that, but we wanted to apply it to this practical system. But if you take one step back, so what is it, why we are doing this at all? So this electronic structure calculations, you use already computational resources to solve a few equations into what's called like self-consistency loops until you reach a system, or you reach a conclusion of your ground state energy, you can say it like this. So the current limitations that, as I told you, that you see examples for small molecules only, which can run on few qubits. But what if you have larger molecules than just hydrogen? And the solution here is what's called like quantum embedding, which is treats specific parts into your system, take a snapshot of it, and solve it on a quantum computer or using quantum, or solve it using quantum algorithm, and then get these results back to the classical workflow. Then you can call it like correct your energies or correct your results. Then you reach this more accurate results. So as this workflow here, this is a hydrogen atom or hydrogen molecule, and then it goes to this classical computer where you do this Hartree-Fock calculations and qubit mapping and all these steps that are needed and to prepare your problem for a quantum computer. And then it goes through these iterations of what's called like hybrid classical quantum algorithms that using some of the calculations without going into so much details into the classical parts and offload fume them to the quantum computer, get results and measure these results and get your result as this kind of dissociation curve, for example. So as a conclusion here, as I wrote below there, that apply this workflow beyond small molecules to large molecules in periodic systems can be difficult at the moment due to large number of qubits. So what this means that you need really to even simplify your problem even more in order to apply it for a bigger system. But before going to a bigger system, what do I mean by systems in, bigger and smaller and things like that? So systems in material science can exist into this more kind of, uh, structures, whether like it can be 0D structures, 1D or 2D, 3D, and maybe this a little image illustrates that a little bit. So for example, if you are just having this what's called like this core shells and things like that. Maybe this when you have like two molecules interacting and you have like a bigger system, or the environment system. So this system we call it like okay, 0D system. Or if you have what's called like carbon nanotubes, for example, this is a 1D system. Or if you have like a graphene sheet or a surface, this is 2D. Or a 3D when you have a slab or you have a structure, iron, for example, is 3D, for example. So in our case here, it's examining a system into this kind of, you can call it like it's a 2D system plus adsorbents on top. So you can consider it, depending on how you describe it, but it is a 2D plus interacting molecules on top of it. But to get a little bit perspective into that, so modeling materials with this aspect is like solving electronic structure problem. And for that, you do it for molecules or solids, depending on the systems that I was introduced in the previous slide. But then you extract some measurements out of that, and this measurements is the outcomes or what you can relate to this material. Either it is if it's a new material, then it is like it can help you when you go to the lab to synthesize them or to know what should be the properties out of that. And these properties can be different. It can be electronic properties, can be, as I said, as I mentioned there, like vibrational or as this picture says, or more of mechanical properties, electronic properties. So there's a variability of properties that you can really get with this simulations. And this simulation is called also ab initio, which means you don't really need an experimental input for that. You just need the structure or the molecular structure of the system, and then these methods could intelligently create or produce results or predictions, material property predictions for you. I want here to give you a little perspective of how much is HPC resources are already used for when it comes to these calculations. So as big systems or big codes here that's used is what's called here espresso, quantum espresso, or VASP here, and there's GROMACS as well. And this is like when you're using like here for the left-hand side was like a Berkeley JIDA, like so this CPU only, or here is GPU accelerated. And this image is actually old, maybe it's like 10 years old. maybe it's bigger numbers right now, I can imagine. And so this is to show you how big is HPC calculations when it comes to material science on HPC resources. So it's a big industry sector already. And this image, I deliberately put it here because it's from like around 13 years ago, which from a system in UK, and where it really even categorize which codes are used mostly into their systems, and big ones. So one of the things that I can see also going forward, that quantum algorithms will integrate with those packages that are highly used. So one of them is actually here called CP2K, which stands for Carpenal 2000, which is a nice molecular dynamics code. It was Carpenal molecular dynamics, but it's also a huge DFT package that has so much functionalities. Yes, so all in all, I wanted just to give you this perspective that these systems require a big amount of calculations or computation power, and it fills already a big portion of HPC time through these famous codes. For example, worth mentioning that Fast Balloon, which is a huge package used widely, consumed like 20% of the resources on that system at that time. So to give more into algorithm point of view, so how QPUs can handle that. So QPUs can be considered as a specialized accelerators where it can enable such hybrid workflow, which can leverage the system, like the strengths in both paradigms. And one of that, in order to do that, you need like algorithms. And one of the algorithms here is called the variation quantum eigensolver, and where the calculations are kind of jumping between classical part and quantum part. And hereby in the left-hand side, it describes the flow between them somehow. So where you need some sort of pre-processing, and this pre-processing, something called like active space design and mapping to qubit, and prepare your ansatz. And to give it a little simplification here, so it's like kind of preparing the initial solutions that you're going to start with, and then you go into this self-consistency loop where you iterate in your solution to reach to the correct solution. And active space here is like the part that you are allocating for the quantum problem to be concentrating on to solve. And this one, you need to be picky in that one and accurate, because you are the one who understanding your problems, and so you specify the active region depending on your literature and your experience into knowing which should be the regions that has the most important parts that will affect the results of your calculation. But also there is a lot of pre-classical calculations that you can do in order to know this in a more accurate way. So you iterate between the two paradigms until you reach your solution, and material science codes that utilize already HPC resources can combine this into action by offloading these calculations, as I mentioned. So to the problem itself. So what's corrosion inhibition and things? So as I mentioned before, like cars and airplanes, cost a lot with the corrosion and things. So hereby I'm just giving you the problem definition as a classical problem definition, as a normal scientist who have this problem and eager to have more of alternatives to that. But then chromium is used as heavily in the industry as a corrosion inhibitor, and chromium is toxic. So there is a move towards more of organic inhibitors, and these organic inhibitors are eco-friendly alternatives. But so that's where there was a lot of research into screening those. And for challenge here is like to predict really the effectiveness of those alternatives. that then you need to do these atomistic calculations in order to reach a verdict about that. And one way of doing that, which is a simple way here for to simplify the problem, is to examine the adhesion power between those alternative molecules or alternative inhibitors on top of the alloy that is forming already the body of your car or the aeroplane, your aeroplane. Then you do like this workflow that can benefit from, the higher accuracy that the quantum algorithm could deliver due to being the quantum algorithm being closer to this like a Jacobian ladder of heaven, so it's more closer to chemical accuracy, and then uh, reports its results back to your classical algorithm and correct for the energies that could be calculated or the energies that is calculated, because the energy term has so many subterms, and this one of these subterms can be calculated from the quantum algorithm. To do this more in a more detailed way, so if you start from the left in this diagram, so you have your model or your materials, and then you have this quantum embedding theory that is taking care of choosing your active space and retreating this when it comes to the calculation to the active space, the environment, which is already calculated by classical DFT as dielectric, as yeah, this is a little bit approximation, but you can consider the effect coming from the environment as kind of dielectric effect coming into your active space. And then after defining the active regions, you go into the self-consistency loop where you have the classical algorithm and then you calculate the electronic properties and correct the values from the quantum algorithm. So simulations here utilize active space to reduce the resources required to model the system on using the quantum resources. Of course, ideal case will be to have everything onto the active space. So you put everything into active space and calculate, but then this will result into a huge problem that will need more qubits or more circuit or higher, bigger or deeper circuit depths than we could afford at the moment. So that's why we need this kind of approximations. And if you are familiar with a method called QMMM, then you can relate to that. It is a good analogy, but it's not the same. But it's a very good analogy to that if you thinking about it from a QMMM point of view. And QMMM stands for quantum mechanic, molecular mechanic simulation, where you treat a small chunk of your system, like this one, using quantum mechanics, and the bigger chunk using classical molecular mechanics, which is cheaper when it comes to computation power. And this allows you to model bigger systems. And this is kind of the case here as well. To get a little bit into depth into that, so you can consider this is like this equation one, which is the only equation here in this slides actually. It's like the energy you're gonna get, and you're gonna get it from several terms, and a few of these terms will be contributed using could be solved into the quantum processor. So if you get to this small diagram here, you perform these DFT calculations, the whole system, and then you divide it into active and environment. So for the active space here, which is will be this region A, it will get the effect, the dielectric effect from the environment. You do this calculation, heterofocal DFT, energy calculation, and so on. You don't need to bother about it right now. You construct your active space, and you have your Hamiltonian, and then you do this self like the VQE with DFT integration. And as I mentioned, there's a specific detail, but maybe you don't need to bother about it right now if you are having it in a general perspective here. But this it relies somehow on the projection-based wave function in DFT. If you want more, if you are so into that within this embedded methods. I think, but of course, this algorithm has variations. So one of the variations about it that I like is called adaptive VQE. And adaptive VQE basically is more of a build or build few ansatz iteratively. And because you have already kind of a predefined operational pool, and this kind of operational pool, you choose it one by one according to your how you are going into your optimization problem or into your self-consistency. So these different pools are ansatz, well known for quantum chemistry, and this ansatz is defined by this theory EuroCC, and you have your choose your initial state, which can help you a lot into going to your winning final state, I can say, or the more stable ground state final state. And you just like if you follow this diagram, you could easily understand it. So you start from the top, initial states, applying that, you're giving like some kind of test trial state or initial state. You measure the expectation values and you see is your calculation converging or not. Okay, not converging. Then you go again to the pool of ansatz and see, okay, can I pick a nicer solution or another solution that could be more expensive but more robust? Yes, you can. Then you go for this kind of ansatz elements, you apply it, and then you see how's the expectation value again, converge it, yes, then you have a solution. So that's a cool thing in adaptive VQE. You can think about it, but I'm not so accurate here that compared to VQE alone, like VQE will go through the, you can call it like through all the solution or this parameters one in one, but this one is a little bit more in series, but this one is more smart that it has a little bit time to think about what should it choose next. This will, of course, get into give you less computational resources compared to vanilla VQE, I can say. But right now, if you're going to the material scientist perspective, that who don't care about these details, but he wants more accurate calculations. So what should they do? Then build the difficult simulation workflow normally, but then identify the important parts of the interactions, because this important part of the interaction are the ones that you probably want to have it into your active space where you get because this part will be the part where you whatever more accurate results you get from it, this will affect your results. Then you're gonna get more insights, and at the end of the day, you're gonna get better benchmarking between the different inhibitors that you are choosing from. So, and then after that, build this hybrid quantum classical simulations using DFT. So you hereby I'm using CP2K code and then integrate it with the quantum algorithm. And hereby I'm using adaptive EQE. To know more about that, to learn more about this, so you can check the paper here, the code here, and also the raw material, raw data. It's published as well, so you can try everything your own without yeah, hopefully it will work out of the box. And there's also a video demo that I had before. But to give you, before going to the demo, I wanted to also to show you that this is a way that I divided my workflows into one in the left as a classical workflow, or one to the right as a hybrid quantum classical workflow. I still don't call it quantum because I still see this, all of what these methods are still kind of hybrid quantum classical methods, and it's not quantum native. And here quantum native is kind of, maybe you heard about it, this cube um, yeah, there's amplitude compute. Like, yeah, there's some quantum native methods that I'm not good at, or I didn't manage to try it yet. But those ones, if we have the right hardware for that, it will make a huge difference probably into these use cases. But let's be back here. So Of course, as I think, more than 50% of your workload is more of a classical things. And hereby, for example, if I want to screen additives, or sorry, not additive, corrosion inhibitors, then I will go to a database that where other people, other scientists have done already this homework for me. So, for example, this core data, which is very nice, the published database for organic inhibitors that and you compare it actually efficiency wise to chromium and see, or no, efficiency wise to how efficient it will protect your alloys. So hereby goes for you through some screenings you can do, and this is like just simple programming over a database you have. Of course, you need here into this case to keep attention to the pH range, and pH range here is important because it differs. For example, if you have one aeroplane that's traveling, probably airplanes are not only into specific line. An aeroplane can be coming from Luleå in the north of Sweden to Stockholm, which is kind of south relatively. So where's the difference in temperature could be 20 degrees or maybe 15 degrees or something. And then after that, maybe the same flight will go to Cyprus and then it's gonna be plus 25. So we have a delta of 40, and of course going up in the air and going down, there's a huge differences. So you need really to take care of that pH ratios here as well. And the temperature ranges as I mentioned. And then after that, I when I was screening those, because it was I don't remember, it was I think around 300,000 alternatives or something like that. So in my filtration, or I also considered the aromatic ring structure screening. And why I consider this detailed, because then I can rely into the pi-pi bonding to have uh, more attraction between the alloy and the inhibitor on top. Get candidates, do geometry optimization, and here for this one, for example, there is another topic called machine learning potentials that is already has machine learning potentials that can accelerate your DFT calculation. Then I don't need to do 300,000 or DFT calculations for that. Then I can use this potential that is giving me quite comparable results to DFT, and then prepare things for the DFT calculations, different basis sets, and so on. And hereby, this is a little difficult because you need to be well aware that a quantum method maybe is not compatible with everything you have. So you need somehow to, in other terms, you to have as Hamiltonians that could be well mapped there and have all the information you need. And then after that, going further to the right, active space selection and thus preparation, and then using your algorithm, like for example here, adaptive EQE. And then validate and benchmark. Of course, you need to validate with classical method here, like for example here, classical DFT calculations with hybrid functionals and non-local functionals. So in order to do this system, so we have the system to the left, we have environment, as I told you, inhibitor, and so on. I wanted to simplify everything. Then instead of aluminum alloy, it's aluminum substrate. So just aluminum. And instead of environment, vacuum, and here the inhibitor molecule. So you see it's so much simplifications here. And I'm choosing also a simple active space of 2 electrons and 5 orbitals for that to make everything more possible for the calculation. So this ends up in this system that you see here in the bottom, where you have the alloy and you have the inhibitor on top, and then it goes to CP2K, have the active space integration with Qiskit. So the quantum calculation is done on Qiskit, and CP2K is having like the classical ones, and then do this in the classical simulator. This is a little detail, but you can go to this reference over here, where it they invented this nice handshake solution or socket-based communication between Qiskit and CP2K, and it's quite very interesting to learn about. And through I think somewhere here I already referred to the code that can integrate both of them. It's integrating what's a library called Qiskit Nature with CP2K, and I made like a clone from it, and I put it there somewhere. Then it to update it if you are using 1.x version of Qiskit. For the people aware of Qiskit, Qiskit 2.0 or 2.x is a little tough to make it working with Qiskit Nature, but if you want to do this, replicate that, then you be using some Qiskit 1.x. I'm not so good in Qiskit, so I don't know. Maybe someone smart can implement that. But I will tell you another alternative at the end of this talk for that. So a few details. Here's some details. CPU I use like 96 cores in the CPU, and I used also for this one for adaptive VQE. I used Qiskit, but also as a simulator. As results, this was a little comparison, but before that, maybe I will can jump into the workflow a little bit. I don't know if you can see right now a YouTube video. Hopefully, yes. No, I don't think so. So this is, this is how you're gonna see the output file. This is an output file from a CP2K log, as you have seen here on the top. That was me presenting it, and just run it on this Linux machine of everything. And then at the end of the day, or no, sorry, at the end of this workflow here, this is the classical part. So all of the DFT iterations. And hereby, yes, eigenvalue occupancy, yes, good, good, good. Maybe I can make it a little slower. Mm-hmm. So yes, good. Canonical orbitals. Yes. So this part is the part where you have chosen the active space orbitals, and there's a way into your input files to really specify. Either you specify them by hard coded, that you know exactly what is the orbitals that you believe this are important to float to quantum computer, or you can leave it to be around the Fermi level, for example. So it's a kind of still trial and error in these ones, plus also experience. And then here's is end of active space integration. I can tell you that this calculation is already a quantum calculation that is done using using Qiskit. And at the end of the day, it could give me this iteration, and it went through one iteration, and it has this energy, and then it contributed to the total energy by this value. Sorry, this has correct. So it made something. Mhm. Maybe I can make it faster a bit. Yeah, and these are the active orbital indices that we have. Yeah, I think in this one I was still redoing the calculation. Let's go back. So have done a few calculations using those methods. So for example, there's this adaptive VQE where the convergency is excellent, accuracy is relatively high to the vanilla VQE, and the runtime time it will take is kind of a medium. But there's also other variations. This comes called stateful adaptive VQE, for example, and vanilla VQE and so on. So you need to experiment for your problem to do that. Uh, yes, this was a little detail how you really calculate this binding energy, where you need to do three calculations. One to do like a calculation for your supercell, and supercell here I mean the substrate and the molecules on top, and then subtract from it substrate and inhibitors. Yeah. So what's about the inhibitors? So it came up with two inhibitors. One is called 1,2,4 triazole and 1,2,4-T3 thiol antimony. And these binding energies coming from them. And you can see a match between the classical DFT and the adaptive EQE over here. I can say also that you need to a little bit take care also of what's called like RSDFT, and this is something else we can talk about later. But you can say this is a proof of concept of that the calculations you can have you can do this kind of calculations that you used to be only classical to do it also with this kind of hybrid approach, classical quantum approach. Yes, I wanted here to give you a little bit comments into that. So adaptive EQ shows good agreement, yes, but also it allows more orbitals that then you can enhance your results because if you can allow more and more input to that accurate workflow, then you could improve your results. But vanilla PQE, for example, has convergency issues due to the manner that it goes through all kind of the ansatz it possibly go through and so on. Less accuracy, of course. But hereby, I can say that if you expand your active orbitals, even with adaptive VQE, you run into kind of a exponentially higher, like or a more complex problem exponentially, in my opinion. Wanted also to give you a little bit snippet about what could be the time distribution between the two of them. So the CP2K calculation would take around 62% of the time, while the casket was 38% of the time in order to do your whole workflow for that. And it seems worth examining this stateful VQE later on. And these numbers here, runtime, is coming from lithium hydride, which is a simple system. This hereby, you can maybe take it later. For that, just how you can really scale and how is the problem scaling, because you have here a number of orbitals, you multiply by 2, this is the qubits you need. And then the classical cost is somehow going with this kind of n to the power 3, and then quantum cost is more like 2 to the power of number of active orbitals you have. And hereby, I wanted just to specify, how can we expand this into other domains as well. So metal oxide frameworks are a good example here that you can examine this. And of course, examining materials for or more techniques for hydrogen storage and electrode interfaces in batteries and so on. I think I will skip this one because I wanted actually to tell you about something more interesting, which, yeah, here's a summary with all the demo and the materials. But I wanted to tell you a little bit of another method called SQD. And this one, I will not give it so much details here, but I can tell you that this method is more robust. And it was out at the end of last year or beginning of this year. And you can have less qubits with this algorithm. It works perfectly as a quantum classical. I tried myself, and it's more noise robust because also it's yes, and this method, without going into much details, it's doing some classical post-processing for different quantum samples that it do. So it provides many quantum samples, and then you get many results. And then after that, you post-process these results using classical methods. Then you get prone to error results. But if you want to know more about it, so I can encourage you that you sign up for our Quantum Autumn School happening beginning of next month, where we have specific talks about these new algorithms. but most importantly, how to implement an algorithm or how to do your own algorithm. Because going forward, we need quantum native algorithms. We need more of smarter ways to deploy those algorithms, implement them, and use them as well. And during this school also, you would have to try things yourself on IQM machine. And we have already in the EuroHPC joint undertaking a working machine called the VLQ, and which is connected to HPC center already. You will learn also about this variational quantum algorithms more and so on. It's free school, so free registration. Please sign up, and here's the links for the agenda materials, and also please follow us on LinkedIn, then you know more about these offerings. And here's a little bit of the school, and I can tell you that, for example, here into this talk on Thursday, I will talk about a successful example of using SQD to run this calculation on a real quantum device, including IQM device as well, which will be featured during the school. But also hereby, my colleague Juan will give you a good introduction about such methods over here, then you're going to be well equipped when it comes to application like this. So hereby there was some interesting resources and some interesting also topics or approaches for that. I can really also encourage you to look at this bootstrap embedding. It's still embedding, but with very interesting implementation and circuit reduction as a result. And thank you.